Okay, so we're here for electrochemical etching. So the setup is very simple. We have a power source here. This one is capable of going from 0 volts all the way to 60 volts with one channel. And if you have 2 channels, it can double it to 120 volts. The maximum power is 400 watts, which is quite high for a power source. So that is the main component, I guess, where we get the power. And these guys are the electrodes. So one electrode is the sample itself. It's called anodic etching. And so the sample needs to be the anode. And we have a counter electrode, which is the cathode in this case, made of platinum. So the way we put the electrode is very simple. So this one is made of platinum.
Why specifically platinum?
Just because it's inert. That's the main use.
Does the cathode erode over time?
The cathode has not eroded at all. It gets dirty. You can see the white is becoming dark. But the metal itself seems very clean. The anode seems to endure more because it's on the anode side, you get the oxidation reaction. So if you have a metal there, it will oxidize, and that's how it erodes. But this one is the reduction side. So if there's any small amount of oxide, which doesn't happen because this is platinum, but if there was any oxide, it will go away. The oxygen will just leave the sample. Okay, so this is the holder for the cathode, which is the sample. And
cathode is sample and anode is platinum.
Sorry, no, anode is the sample. Maybe I reversed them. But this is anodic etching, so this is the anode. The sample is the anode. The cathode is the platinum. And actually, it's confusing because the cathode is actually connected to the negative of the power source, and the anode is connected to the positive. So the sample here is simply gallium nitride film, that N-type, N-doped gallium nitride film grown with our MOCVD. Usually for this, I usually cut most samples into 1 by 1 centimeter size. This one is roughly 1 by 1, a little bit more, maybe 1.5 by 1, which actually will make it easier to put it. Actually, the larger the sample, the easier it is. And you want the metal side. So this is indium metal, indium contact. So you can see I put just some indium beads on the surface. I press them and then I anneal. Maybe you would like to see that on the camera. So indium contact on the film.
Why do we need that indium?
Just to form contact with the sample. So because you want the current to flow freely inside the sample.
So if the sample is not conductive, this will not work, right?
Yes, if it's insulating, then you will need extremely high voltages, and then maybe you'll just break down the sample before you can etch it electrochemically. So yeah, we just put it right here.
All these parts are made of Teflon, right? Are they custom made?
I don't know what this is made of. It might be Teflon, but they're not custom made. We bought them online.
Ah.
Yeah. Previously, when I started doing this, I custom made a lot of parts, and then decided to look for some parts online, and actually they are way better than the ones that we make ourselves.
I think the material is Teflon because
it might be
resistive.
very inert, right?
Yeah.
But the cap is it's like a ceramic, so it might be some oxide. I'm not sure what it is. And these electrodes seem like a copper alloy, maybe brass or something. Yeah. So we usually put them facing each other, so the film facing the electrode to for the electric field to be like to go through the sample. Let's close this one. Okay, so that's basically how we set up the sample. Usually, I also add a little bit of Teflon tape to protect the anode from erosion. So usually, I keep a little bit in here. Let's see if I can do this. Actually, let me remove it. It's going to be easier if I just remove it. Okay, so this is the sample. Just wrap it around it. So this one is just to make sure that the metal does not touch the liquid. So if the metal touches the liquid, you'll have current flowing through the liquid, so you'll end up doing electrolysis instead of electrochemical etching. So you want to minimize that. You cannot avoid it completely, but you want to minimize electrolysis. But actually, if you're doing research in electrolysis, then maybe you want to do that. Yeah, so I just wrap it a few times around. So you can see there are O-rings that you put here to hold it in place, to hold the sample in place, or the electrode. Now, basically, what we do is we choose our electrolyte material. I have used phosphoric acid, and I had the most success with it. But we can also use any other kind of acid or base. I have tried also potassium hydroxide, KOH, and I also have tried hydrogen chloride. I think today I will use hydrogen chloride because I have the solution prepared, so I'll just dilute it and we can use that. So from here, this is phosphoric acid, and this is hydrochloric acid. So I will use hydrochloric acid, and I would like to dilute it. So can you give me some space here? Also, here we have cold water, hot water. This is normal tap water, and this one is RO water, which is high purity water. So I think I will dilute 50-50, 100 mils of water and 100 mils of the acid. I'll put them inside the beaker. Actually, it's usually better to first prepare your main solution and then you add to the beaker. But since I'm doing this just for training, I'm not paying attention to the concentrations. So this solution is 0.36 molar hydrochloric acid. Of course, you need to decide first what concentration you want to use. And you should have your stock solution on the side. And then if you need, you add as much as you need, but the way I'm doing it is just for demonstration. So I will just put like 50-50 solution, and if it's not enough, I will add more liquid just to make sure it reaches the sample. Normally, you want to prepare more solution. So this is hydrochloric acid. You need to be careful with it. It's not very dangerous, but it's also, you don't want to touch it. Roughly 100 mils. So all of the acids and bases are all stored in this corrosive chemical cabinet. Yeah, as you can see, the sample is suspended well in there. The liquid is not going up to the metal in the anode side, and it's covering up all of the cathode. So this is a good amount of liquid. So and the sample is facing the cathode, which is also good. Now the only thing missing is a stir bar. This is a magnetic stir bar. Normally I give it a rinse or a wipe to the acid. So this is also DI water. So now we have the hot plate or the stirring plate. Just because I know sometimes people put chemicals on this, I will remove the aluminum foil. It might be contaminated, so I don't want to deal with that. We will dispose of it in the proper waste, chemical waste. We can start stirring. I put it at 500. Usually I put it around 500, but sometimes we change the speed based on our needs. So this is the aluminum foil, and this is the chemical waste. So I'll just drop it in the chemical waste cabinet. Bin.
Have you tried using higher temperature?
Yes, I have tried just below boiling temperature. I never went above that. I just like 95 degrees Celsius. If I do higher temperature, I will show you. I usually take this one. I fill it with hot water. Usually the best source of hot water, I can just go outside to the
hot bath.
To the water. I take it in a separate cup. So you don't want to contaminate anything, of course. Take it in a separate cup, and then you bring it inside, and then you pour it here, and then you can put the beaker inside of this one. So normally it will look something like this. You can put this inside. You fill this with water, and if you want to monitor the temperature, so this temperature is the temperature of the metal. And the temperature of the metal is almost always higher than the temperature of the liquid. So to monitor the temperature of the liquid, you need a thermometer, and we have those over here. Normally, I would suspend it from this holder. You can, of course, set it up. Usually, I lift this one all the way to the top, and then I hold it to squeeze the thermometer. And the best thing you can do is you don't want the mercury to touch the bottom, because also you will touch the hot surface, so you will measure the metal. You want to measure the liquid, so you suspend it in the middle, just right here in the middle of the liquid or the hot water. You can also use oil or another fluid if it has. It has something like this.
Yeah,
So yeah, you can twist this one like this. You can use this one to squeeze it, something like that. So it's like suspended. Of course, you can fix it inside your liquid. Like I can bring this one to the back, lift this one up, and so on. But since I don't want to change where things are, I will just, I'm not going to do that. Yeah, so we have a few thermometers here in the lab. But today I am doing at room temperature, so only directly like this. Here I pass these cables. So we have a red and a black cable. The red is connected to the positive. So the positive is the anode, so the red goes to the sample. And the black is the cathode, which is the negative electrode on the power supply. And it goes to the platinum electrode. So we have not turned on the power. Yes, so we have power, and I can turn it on. So still, this is not passing. No current is passing. It's that one is not on yet. I will bring a flash drive I will show you. We can extract the data. You can plot the current over time and the voltage over time. So I will bring a flash drive so we can store that. For here, I will show a demonstration. So we can just put this here. Yeah. So to output the data, I think, no, not the output. To get the data, we need to go to the data logger. It's called the data logger. This one will this one will record the data. So you go here, and then you go to properties. And then since we are using the left channel, which is marked with a yellow color, we want to only record the data from the yellow channel. So we have V1, the voltage of the first channel, I1, which is the current of the first channel, and P1, the power of the first channel. Normally, I just take the voltage and the current. If you take the product of the two, you get the power over time. So you can just record the V and I, and then get the power later. So we go. So we uncheck the green one. So it was going to be recording the voltage of the first channel and the voltage of the second channel. So I uncheck all of the green ones, and I only check the first channel voltage and the first channel current. So this is on the left side. There are a lot of settings here that you can change. But so this the numbers over here next to the channels will determine the scale of the data logger. But normally I just use auto scale, which will correct for that. Here there are some settings related to the division, like in the time scale. You can also play with that. Normally I don't change the default.
So how do you make it in auto scale?
I will show you in the other page. Where is the pointer? Yeah, and there is also the logging settings. You can choose the duration of your logging. There's hours, minutes, and seconds. The default is 0 hour, 0 minute, and 30 seconds. So of course you want to change that to log more. So you always want to log more than the duration that you plan. So if you plan on doing this experiment for 1 hour, you want to log at least 1 hour or maybe a little bit more. So for the training, I will log maybe just 5 minutes. OK, 5 minutes. And here we have 30 seconds. I will leave that. So we can always use a little bit more, few seconds of recording.
How do we define we need 1 hour or 5 minutes or something like that?
This one is based on, basically you need, it's trial and error. So it will depend on the resistance of your sample, the chemical resistance and the electrical resistance, and how strong your electrolyte is. There are many factors that will play into that. So basically, normally you want to do the testing yourself until you get the correct recipe for your application. Yeah. So, but this one is the good thing about this one is that it's capable of achieving very high power. So if you think your previous experiment was not sufficient, you can always increase the voltage.
Right now, I think the channel 2 is activated.
That's okay. We can fix that. But they're both turned off. That's okay. When you turn it on and off, you can click here. I think this is related to the controlling the channel 1 or channel 2, but we'll go back to the main page and we can see how it is. So normally I only change the time and what data we log in this page. And later I click File Selection. And you want to change the save path to be external. You can also choose the name of the file. So file name, there's a button called File Name. I can clear all, and then I can name this something, A, B, C, something. So any name you want. But this will not be the main file. This will have all of the data that you need, but you cannot read it with your computer. Once we are done, you need to convert the data into a CSV format so you can read it with your computer. You convert it also using the power supply itself. Yeah, so file name, there's a button here, and then I can write the name of the file. So it's called abc.dlog. This dlog is only readable by this machine. So let's say we are done here. So I put all of the information that I need to collect data from this experiment. So I click back and then back to the data logger page. So in this page, you can start the recording by clicking stop. It's called run stop button. So I click on this one. Once I click, it will start recording until the end of the experiment. So I put it as 5 minutes and 30 seconds. So once I click, it will start ticking time, 5 minutes and 30 seconds. Now it's still not, there's no power. So I need to go back to the main page, set the voltage and the current. So let's say I will put 10 volts, enter, and then since we are controlling mainly the voltage, and the current will just follow. It's easier with this setup. It's easier to control the voltage, and the current will just follow. So that's what I normally do. I set the voltage that I need, and I put a limit on how high the current can get. Normally, we will not get to 1 amp. So just for the sake of safety, I'll put 0.1 amp. So this is like 100 milliamp. Still no current flowing. Once I click on, now it is at 10 volts. The experiment now just started etching. And if I go back to the data logger, so if I click on the data logger button, you can see there is some signal. There is a constant voltage, and there is a current. You can always auto scale. There's an auto scale button that will fix basically what you can see.
The current is quite low, right?
It's extremely low, but that's good. If you get a high current, then yeah. So I set the maximum as 100 milliamp, but the actual current right now is actually 0.1 milliamp. So it's extremely low, and that's fine. Depending on your settings, the electrolyte and the voltage, you can get different values. But if you get a high value, then there's probably some leakage through the liquid. So maybe you're just doing electrolysis instead of etching. So now this one is outputting the voltage to that. And for the duration of like 5 minutes, you can wait for your experiment to be done. We have constant stirring, so everything is good. And it's inside the fume hood. So if there is any toxic gases that are generated, they will be taken by the fume hood. I think that's basically the basic process of this experiment. So I can stop it, and I can maybe show you some more information about the power supply. After that, I will test you with some questions about this training, basically.